Hey everyone, grab those digital notebooks and let's jump right in. Welcome to this fully guided explainer where we're going to master absolutely everything you need to know about polygons. We are building this straight from the ground up, step by step, using the very best examples directly from our source material today.
Now check out this absolute beast of a diagram from the source text. It's called the machine of angular measure. It looks incredibly complicated, right? You've got gears, overlapping lines, protractors everywhere. But listen, by the end of this lesson, you're going to be able to navigate even the most complex compound shapes like this with total ease. So can you find the missing angle in any shape in under 10 minutes? Stick with me and I guarantee you will.
Here is our agenda for today. First, what is a polygon? Second, convex versus concave. Third, summing up interior angles. Fourth, the rules for regular polygons. And finally, a tough practice challenge to bring it all together.
All right, section 1. What is a polygon? Let's lock down the basics before we do any actual math.
Think of a polygon as literally any shape you draw with a ruler that completely closes in on itself. No curved edges allowed. If it has a curve, or if there's a gap where the lines just don't quite meet up, it's not a polygon. Simple as that. Our source also highlights a really crucial term here, the diagonal. A diagonal is just a straight line segment that joins two non-consecutive vertices. Basically, you draw a line from one corner across the inside of the shape to another corner, not along the outside edge.
Now you've got to memorize these specific names. Everything from a 3-sided triangle all the way up to an 8-sided octagon. Why? Because the name tells us exactly how many sides and how many vertices, or corners, we're working with. And knowing that exact number is the key to unlocking every single formula we're going to use later on.
Moving on to section 2, convex versus concave shapes. Let's see how one single angle changes the whole game. Our source outlines two main types of polygons, convex and concave. A convex polygon is basically what you think of when you picture a normal shape. All of its interior angles are neat, tidy, and less than 180 degrees. But a concave polygon, that one's a bit of a rebel. It has at least one interior angle that's greater than 180 degrees, which we call a reflex angle. If you trace the outside, a portion of the shape literally caves in on itself, and that caved-in corner creates that massive reflex angle on the inside. That's what makes it strictly concave.
Let's see a quick trick using a great quadrilateral example straight from the text, where the angles are given to us as algebra. We've got 12x, 5x, 50x, and 5x. Let's work through it. We know a four-sided shape's angles always sum to 360 degrees. So, step 1. We add them all up to equal 360. Step 2, we combine our like terms to get 72x equals 360, which means x equals 5. Now why did we even do that? Because we need to test if the shape is concave. In step 3, we look at the biggest angle, which is the 50x. We plug our 5 back into that. 50 times 5 equals 250 degrees. And since 250 is clearly greater than 180, we found our reflex angle. The shape is definitively concave.
Okay, section 3. Summing up interior angles. We're calculating the total so we can solve much larger shapes.
Guys, this is the absolute master rule of polygons. The sum of the interior angles equals n minus 2, multiplied by 180 degrees. Now n always represents the number of sides. But why do we subtract 2? It's actually not just a random number. Our source perfectly explains that if you pick one corner of a polygon and draw diagonals to every other possible corner, you split the shape into perfectly sized triangles. And the number of triangles you create is always exactly 2 less than the number of sides. Since every single triangle holds 180 degrees, multiplying those triangles by 180 gives us the total degrees for the entire shape. It's brilliant!
Okay, let's put this to the test with an example from the source document. We have hexagon A, B, C, D, E, F, and it has a missing angle represented by x. But before we can solve for x, we absolutely need the total. So pause the lesson right here, grab some paper, and try this yourself. Calculate the total sum of the interior angles for a 6-sided hexagon before we set up the algebra. All right, let's walk through it together. Step 1, we plug n equals 6 into our formula. 6 minus 2 is 4. 4 times 180 gives us a total sum of 720 degrees. Great. Now for step 2, we add up all the given angles. X plus x gives us 2x, and the regular numbers add up to 480. We set all of that equal to our new total of 720. Now, many students make a mistake in this step by completely forgetting to subtract 480 from both sides before dividing. But as we solve this out correctly, we subtract 480 to get 2x equals 240, leaving us with our missing angle x being exactly 120 degrees. Beautifully done.
Section 4. Rules for regular polygons. These are special, super powerful formulas for perfect shapes.
Be careful here, because the crucial point is that a shape must have both properties to be considered regular. The source is very clear about this. All sides must be exactly equal in length, and all interior angles must be exactly equal in measure. If a shape only has equal sides, like a rhombus, it's not regular. It needs both, just like a perfect square or a perfect equilateral triangle.
Because these regular polygons are perfectly balanced, we can easily find the measure of just a single interior angle. This formula right here is literally just our previous rule for the total sum, but divided by n, which is the number of angles. We are just taking that massive total pool of degrees and ensuring every single corner gets its exact equal share. Additionally, the source notes a fantastic shortcut. A regular polygon always has exactly n axes of symmetry. So a regular hexagon with 6 sides, boom, it has exactly 6 lines of perfect symmetry. Time for another quick knowledge check directly from the lesson text. If you have a regular pentagon, meaning 5 equal sides and 5 equal angles, what is the exact measure of just one of its interior angles? Grab your pencil, pause the lesson, plug n equals 5 into our brand new formula, and let's see what you get.
All right, let's see the math in action. Step 1, we find the total sum first. 5 minus 2 is 3, and 3 times 180 is 540 degrees total. Step 2, because it's regular, we take that 540 and divide it evenly by the 5 corners. 540 divided by 5 equals exactly 108 degrees. This just brilliantly illustrates how the total degrees are split perfectly to give us 108 degrees per corner. Oh, and as a bonus, because it's a regular pentagon, it has exactly 5 axes of symmetry.
And finally, Section 5, the final practice challenge. We've built up our toolkit, and now it is time for the boss battle. Take a look at this challenge pulled straight from the homework section of our source. This is a common exam question, right here. It joins 2 regular shapes together, side by side, a regular hexagon and a regular pentagon. It looks incredibly intimidating because they only want the measure of the empty gap between them, angle AIB. But don't panic, we have every single tool we need to solve this methodically. Look really closely at vertex A. That's the central point where the hexagon and pentagon touch. There are 3 distinct angles forming a complete circle around that point. The inside corner of the hexagon, the inside corner of the pentagon, and then that empty gap, angle AIB. So pause the lesson right here. Remember what a full circle of degrees adds up to, use your regular polygon formulas for the 2 shapes we just learned, and see if you can find that gap. Okay, let's write out the logic step by step. Step 1, we use our formula to find a single interior angle of that regular hexagon, which is 6 minus 2 times 180 divided by 6. That gives us 120 degrees. Step 2, we actually already solved the regular pentagon earlier. Its single interior angle is 108 degrees. Step 3, we know that a full rotation around vertex A is a perfect circle, which means it's 360 degrees. So, step 4, we just subtract the angles we know from that total circle. 360 minus the hexagon's 120 minus the pentagon's 108, and that leaves exactly 132 degrees for the gap. Outstanding work. Great job mastering polygons with me today. You now have the formulas and the step-by-step logic to literally conquer any geometry problem from this unit. But I can't let you leave without a final provocative thought. For your homework, see if you can calculate the new gap angle if we completely remove that 5-sided pentagon and instead attached an 8-sided regular octagon to that hexagon. What happens to the math then? Go test it out in your notebooks and keep learning.